Thank you for tuning in, and thank you to the organizers for the opportunity to present this work. I'm Fondrie, and today I'm excited to present learning compact representations of high-resolution tandem mass spectra without supervision. I want to start by highlighting some tasks where it's critical to use mass spectra as input into machine learning models. One of these tasks is de novo peptide sequencing. Another one is clustering mass spectra, where we're interested in mass spectra, finding groups of mass spectra that could have possibly been generated by the same or similar analyte. Another slightly different task is embedding mass spectra, where we try to embed mass spectra into a latent space that has some sort of meaning. Another one is learning data-driven score functions, which will potentially let us detect analytes with greater power from the mass spectra that we collect. And lastly, there's predicting properties of the mass spectrum. For instance, whether it's identifiable by a common method that you use. For all of these methods, it's critical to be able to represent the mass spectrum in a way that the machine learning model can use. So when we look at a mass spectrum, we can think of it as a bag of peaks. So here I have just an example mass spectrum. When we look at what a mass spectrum really is, we see that it's a collection of two tuples. Each peak is represented by a mass to charge ratio and an intensity value. And so this bag of peak structure is not one that lends itself to being easy to use for computational tasks. In fact, most machine learning methods will require that a mass spectrum is in the form of a vector. So that begs the question of how can we represent a mass spectrum as a vector? One common way to accomplish this is to discretize the mass axis to yield a vector. So here I have an example mass spectrum, and what we can do is define a bin size in which to bin the mass axis. And so here I've chosen a relatively large bin size such that you can see that multiple peaks often fall into the same bin. Here I've just kept the most intense peak, and that becomes the intensity for that bin. And together these bins become a vector representing the mass spectrum. Now you can see with these large bin sizes that we've transformed the mass spectrum into a vector, but we've lost information in the process by aggregating multiple peaks. To analyze this, we could use a smaller bin size. Here I've used a smaller bin size where we see typically only one peak falls into a given bin. However, as our bin sizes get smaller and smaller, we introduce more and more bins that don't have any peaks in them, increasing the sparsity of our vector. We also introduce more edge effects, where minor variations in the measured mass charge ratio for a peak may cause it to fall in one bin or another, just depending on those variations. And then when we're thinking about inputting these vectors into machine learning models, although they are sparse, many types of machine learning models are not suited out of the box to work efficiently with sparse vectors. And so when we look at, say, a mass spectrum from MZ 0 to 2000, using a low-resolution binning strategy of, say, 1 m/z size bins would yield a vector of length 2000, but a high-resolution binning strategy would then yield a vector of length 200,000, which becomes really unwieldy, especially if you're trying to handle it as a dense vector on a GPU. And so one of the questions we wanted to ask was, can we adapt methods from natural language processing to generate compact vector representations of mass spectra? And specifically, what we hope to leverage is the transformer architecture, which has taken the natural language processing field by storm recently. Now, transformers learn from sequences. The basic makeup of a transformer model looks something like this, where you have an input sequence, and that input goes through some sort of embedding process, become a vector, which is input into the transformer layer. Now, the core of the transformer layer is this multi-head attention mechanism, which I'll talk about later. But it goes through this multi-head attention, and then the different attention heads are fed through a feed-forward network to combine them again. And after going through all of this, we get our contextualized embeddings for all of the items in our original sequence. And so just to illustrate how this works practically, I have a sentence here where we have 4 items in our sequence. We have mass spec is awesome. So each of these will go through an input embedding and then go through the transformer encoder. And then each one will have its own new contextualized embedding that is the output from the transformer encoder. And what we hope is that these types of models have learned to associate, in this sentence, awesome with mass spec. So the model has learned that mass spec is indeed awesome. And so like I mentioned, the core of the transformer model is the multi-head attention mechanism. And what that is in this transformer encoder is a form of self-attention. And self-attention is really what adds context to sequences. And so in the original transformer paper, they describe their self-attention with this equation, where Q, K, and V stand for queries, keys, and values. And those end up being derived from learned weight matrices, which is a major thing that the transformer learns. And so the ways I like to think about this are that the queries are, if I focus on this item in the sequence, the keys are, how much does its meaning depend on each of the other items? And lastly, the values are the item's representation without context. So given the query, key, and the value, you can add context to the values. And so we can actually kind of think about how this would work in the case of a sentence again. Here I have a simple sentence repeated with itself, which is proteomics is cool and metabolomics is too. And so if we think about the first word, what words it derives its meaning from, if we think about this, it would be is and cool here. So we have cool being something that helps define proteomics in this sentence. And so we would expect that that would have a high attention. If instead of sentences, what if we were actually tried to add context to peaks in a mass spectrum? And so the problem might look something like this, where high attention weights would indicate an amino acid, the delta mass of an amino acid in say a peptide mass spectrum. Or again, in a peptide mass spectrum, perhaps a high attention weight would indicate a complement ion for say the complement Y ion to a B ion that's observed. And so we wanted to set out to build these types of transformer models that could learn the relationships between peaks in a mass spectrum. And the way we decided to do that is to learn a representation that preserves the similarity between mass spectra. And so the measure of similarity we chose was a dot product between mass spectra, or between bags of peaks. And this has been described by many people previously, but we've called it the generalized scalar product. And the basic algorithm is this. You start with the most intense peak in a mass spectrum, or in the two mass spectra you're trying to compare. You find the highest intensity peak within some defined tolerance in the other mass spectrum, and then those become a pair, and you multiply the intensities of those peaks. And then once two peaks have been paired, they can't be used again for the rest of the calculation, but you iterate through all of the remaining peaks and sum those results. And so this is essentially a dot product that allows for a little wiggle room on the MZ axis. And so here's just, in my example mass spectra, what all the peaks look like once they've been paired. And so we wanted to use this generalized scalar product as target for our model to learn. And so our goal was to predict the GSP between two mass spectra. And to do this, we start with a single mass spectrum. Again, we can think of a mass spectrum as a collection of these tuples, where each one is described by a mass to charge ratio and an intensity. And so these are the items in our sequence. And we're going to send these through we're going to encode these using a sinusoidal coder. And this is something that I borrowed from, or adapted from the natural language processing field, in particular from the original transformer paper here. But the way encode Z values is as sinusoids from with wavelengths that range from 0.004 m over Z to 4,000 m over Z. So if we just kind of visualize this across a wide range of masses, here the x-axis is m over Z, and the y-axis is the features that would come out from this encoder. What you can see is that you have really high frequency features, and you have some really low frequency features as well. And so these long wavelength features, those would cover longer mass differences, and the smaller wavelength features would cover the really fine details you see in mass spectra. And so if we zoom in, you can actually see that this pattern goes down well into the sub 0.1 MZ range. And so this is how we're encoding MZ in particular, and this is combined with the intensity using a linear layer to yield our input embedding for the transformer encoder. And so then we also add a learned spectrum vector, and so this is something that's learned during model training, and it's what will eventually define how our spectrum is represented as a whole. And these go again through the transformer encoder layers that we talked about. And this will generate a collection of peak embeddings. But critically, from this learned spectrum vector, we'll also get a mass spectrum embedding, which is what we want to use downstream. Now, the way that we actually learn to predict the GSP is actually using a Siamese transformer architecture. So we actually have another copy of this same network with shared weights, where we embed a different spectrum. Here it's spectrum Y. Then we concatenate the embeddings for these two, send them through a feed-forward neural network, and the output of that neural network is the predicted GSP between those two mass spectra. And our loss function is then the mean squared error between the true GSP, which is our target, and our prediction. And so this is how we're going to train our network. And the critical thing here is that we don't rely on any external labels, like, for instance, relying that each mass spectrum has been identified or has been annotated with a peptide or something like that. Instead, we could use any pair of mass spectra to train this model. And so that's kind of what we did. We gathered 95 million mass spectra from the Massive repository, and we downloaded them from Massive using a tool called PPX if the MDML files were originally converted by Massive. This was just to ensure that the MS2 spectra were centroided, so we didn't end up with any profile mode spectra. And then we used a tool called Parametric to select for high-resolution spectra, or high-resolution tandem mass spectra, by looking for ones that where Parametric found a fragment bin size that was 0.02 MZ or less. And so what we found were just with the small sample that we started with were 20 projects that we used as a training set with over 80 million mass spectra in them. 3 projects we used as a validation set. And then our test set has over 11 million spectra from 7 different projects. And so what we found was that compact representations using this type of model were actually sufficient. We found that as you increase, you don't gain much by increasing the embedding dimensions here. Here, the y-axis is the mean squared error, and the x-axis is the embedding dimension from our model. In fact, if you get too big, we actually observe mode collapse, and then eventually it's too big. The model becomes too big to fit on a reasonable GPU. And then when we train a three transformer layer model, this is what our validation loss looks like, where we get a significant decrease in the mean squared error for the validation set, and achieve a loss that's much lower than if we did a low-res binning strategy, and not quite as good as if we had done a high-res binning strategy instead. again, with 32-dimensional embedding. And so what we found is that these 32-dimensional embeddings outperform low-res binning. We find that when we plot the true generalized scalar product against the predicted generalized scalar product from our transformer model, we get a plot that looks like this. High-res binning looks a little bit different, or looks a little bit better than the results from our transformer. And then when we do a low-resolution binning strategy of approximately a 1 Dalton bin size, we get an inflated predicted GSP due to mismatching peaks in these binnings. One of the cool things is that our embeddings appear to capture fragment patterns in the data. Here I embedded a phosphoproteomics data set with about 56,000 spectra in it. And this is what the UMAP embedding of our embeddings look like. And you can see that there are these kind of two arms out by themselves in this plot, and then a big blob and some smaller structure around there. And if we color by whether a spectrum was identified with identified during our database search or not, you can see that these tendrils had very few spectra identified in them. And if we look at we can look at how this relates to the precursor M over Z, where you can see as you move up in this plot that the precursor M over Z increases. And you can see that these are very high mass. These tendrils are very high mass, and they're also a very high charge. And one of the things we concluded is that these are just analytes that are washing off the column at the end of the run, which is kind of to be expected that they wouldn't be identified. But the interesting thing is that we were readily able to see that these were different types of spectra just from our embeddings that we had learned. And so just to conclude, I hope I've relayed that there are many useful tasks that need mass spectra as input, and that these binned representations of mass spectra can be large and inaccurate and difficult to work with. The transformer architecture that I've presented here allowed us to model the relationships between peaks in a mass spectrum, and that these embeddings capture important patterns that can be used as input for new tasks. And so what we're planning on doing is using a full transformer model, not just the encoder, but the decoder as well, to do de novo peptide sequencing, and then to delve into learned score functions for proteomics and getting beyond some of the ones that have been developed by hand in the past. And so with that, I'd like to thank you all for listening, and thank Bill Noble and the Noble Lab and Elena, and thank you for our funders. And with that, I will take any questions.